Hi, welcome to LSEC tutorial. LSEC stands for Elastic Management of Security Applications on Virtualized Infrastructure. So a very quick overview of LSEC system. Here we have user applications which are running, and the flows are going from user applications to a destination network, let's say. And we have to run virtual network functions in the cloud environment, um, running in cloud infrastructure here. These are virtual network functions that come and go on demand. So there's an auto scaling that is happening here. So our LSEC system basically makes sure that we can elastically manage these resources. This is horizontal scaling. And also, since these are security virtual network functions, so it also has an attack analyzer component where it analyzes the attacks that are happening in the network, which has a global picture. Attack analyzer has a global picture of the different type of traffic that is coming to virtual network functions, and it makes decision about what to block, what type of traffic to block or not. And this information is forwarded to the forwarded controller, which then updates the forwarding rules in the network. Okay. We also have this tutorial is about implementation of LSEC system on GENI Testbed. So we have this tutorial, a very detailed tutorial about how to implement LSEC system. So on the GENI testbed we have a network like this where we have source and destination, OVS switch, and multiple visual network functions and a controller node. The way we have implemented LSEC is shown in the figure here. So LSEC is basically in this area of the network where we have a Snort IDS running on each of these visual network functions, and we also have a monitoring application that is running here. This is the RENA monitoring application. All the updates from RENA application is being sent to the RENA app running on the controller node. So basically we do load balancing based on the CPU load that we get from RENA application here. And this information about CPU load on these VNFs is sent to the PID controller, which then elastically manage where to send the traffic. If the traffic is less, only one of the VNF will be used. If the traffic increases, it scales up. And again, if the traffic goes down, it scales down. Okay, so that's the responsibility of the PID controller, and it tells the OVS controller where to send a flow. And again, if any of the VNF detects any attacks or certain kind of traffic, it informs through RENA application, it informs attack analyzer the type of attack or type of traffic that it is receiving, and attack analyzer make a decision about which hosts to block, and this is given to OVS controller and then in the form of attacker list, where OVS controller then takes this list and makes sure that these traffic coming from these hosts is blocked. Okay, so let's go on and do a hands-on tutorial. So I've already set up this setup in GENI. So as you can see here, I have a controller node on a separate slice and the network here on a separate slice. And I have these are 4 different VNFs, these ones here, which are running here. So each of these VNF is running Snort IDS here. They're also running RENA, but I'm not showing it here. They're running in the backend, RENA monitoring application basically. Here on the controller node, I have the RENA application here getting all the information. This is same as the one I showed here, these RENA applications. So this is this part I'm showing here. So here I have the RENA application which is getting the CPU load information. For example, here this is like for 4 different CPUs, what are the CPU loads here, and this is constantly getting this information. This is the attack analyzer, which is this part here, this one. This is over here, and it currently doesn't have any attacks, so it's not showing anything. This is the PID controller. So basically it tells that currently the load is set to be 50%, so if the load becomes more than 50%, only then the traffic is being sent to the other side. So every few seconds it does the load balancing. So it says that currently the load on the system is very little. As you can see, this is the percentage current load in terms of percentage CPU usage on VNF1, VNF2, VNF3. And what is the percentage of traffic that is being sent to the next VNF. So currently there is no traffic being sent to VNF2, VNF3, VNF4, so there is no load on VNF1. We also have the real-time graph here. This basically shows how the load is changing. This is changing over time. Okay. So as you can see, this graph is moving, but everything is around 0% here. This is the OVS controller, which is basically making sure that the attackers are being blocked, and the traffic is being elastically managed based on the PID controller. Okay, so let's run now some background traffic. So we have this script which basically generates background traffic. You can go and update its parameter. That are the way how you update the parameters is given in the tutorial. But for now, I will just run the traffic generator. So I'm running the traffic generator now. You can see that there is new flows are being sent, and these flows are being put. The open OVS controller is putting open flow rules on the OVS switch. Here you can see all the traffic is currently going to VNF1. Reason being, when you look at the load here, so this is the load graph. You can see that currently the load is less than 50%. So all the traffic is going to VNF1. But over time, you will see that the traffic will increase as the traffic is increasing and it goes above 50%. Some of the traffic will go to VNF2, some of them will go to VNF3, and so on. And then if we want to scale it down, it will elastically scale down based on the PID controller again. Okay, so for now, I will leave this alone. What I'm going to do is I'm going to do attack on the system. Okay, so the way I will do the attack is, again, I have a script on my laptop which I will run. It's an attacker.py. The details of the script are in the tutorial. I'm just going to run it. So what's going to do is it's going to generate an attack. This attack is going to be detected by the snort instances, these snort instances running here. This information will come on the attack analyzer over here. It will show the IP address which is being blocked, and this guy over here, OVS switch, is going to block them. So currently, if you look at source 1, this is source 1, and if I ping destination, my pings are going through, right? So I don't want this ping to go through if this source 1 is the attacker node. Okay, so that's what I'm going to do. I'm going to make a port scanning attack, do a port scanning attack on source using source S1. So now I'm going to do port scanning attack. So it's currently removing some old files, and now it's doing the nmap attack. So if I'm on the controller node, you can see here that I will soon detect this attack. Okay, so here you can see IP is being blocked. So you can say this IP has been blocked. Okay, that's because the attack is being detected. So if I go again to source 1, because I use source 1 to create an attack, so if I do ping, my pings are not going through. That's because this IP address is blocked. The system quickly detected it. Okay, and if I go back to the attacker, so once the attacker does an attack, it waits for 2 minutes. And only then it prints the stats, which is basically telling how long it took for the system to detect the attack. So we're going to wait until it prints out how long it actually took to detect the attack. We can see that the attack has been detected here, but again, the script actually has to wait to make sure that the attack has happened. Only then it can read the log files to see how long it took to detect the attack. So here you can see the CPU load on VNF1 increased, and once it reached 50%, some ratio of the traffic is being sent to VNF2 now. So it's elastically scaling on its own as the traffic, incoming traffic, is increasing. As you can see, the VNF2 is now increasing the load. As you can see now, it's almost reaching 50% now. Since it reached 50%, some ratio, which is only 4% right now, is being sent to VNF3 now. And now VNF3 you should see an increase spike here on VNF3, since some ratio of the traffic will go here. Still 1.2%, so it's very little, but with time I think you will see it very soon. It will start increasing. So it's now 4%. So definitely, as you can see, a spike coming up here. And let's see how it goes. I will fast forward it now. I just closed the traffic generator. So now the traffic should go down, and the system should elastically scale down. Now you can see that initially VNF1 load went, oh, initially since the load gets less, um, the load on VNF4 first went down to 0 or almost 0. Then you can see the load on VNF3 went down. Now you would see load on VNF2 would go down, and at the very end load on VNF1 will go down. So this is again elastic scaling. So initially, as the load on VNF1 increases, you start using VNF2, and then you start using VNF3, and so forth until you reach VNF4. And you can, of course, go on with this with as many VNF you want. For this experiment, we have only 4 VNFs. And now as the load is going down, first we release VNF4, then we will release VNF3. We have already done VNF3. Now we're going to release VNF2, and in the last we're going to release VNF1 as well. So VNF4 is released here, VNF3 is here, VNF2 is almost done also. So VNF2 is also done. Now the last VNF1 is left. Now you can see the load is 0. So there is no load anymore on the system since there is no background traffic. And if we go here and check, there is none of these VNFs are receiving any of the traffics right now. Okay. Thank you very much for taking your time out.